Welcome to Truth in Structures. I'm Joshua Supreet. So, here in this channel, I'll be talking about structural design in detail. So, mainly, I want to cover all kinds of concepts and structures which might help you to get more employment opportunities in the UK. So, here I'll be beginning with a prologue. So, this will consist of two topics: geomechanics and theory of structures. I'll just brush up a little concepts from geomechanics, solving a few problems here and there. Before moving on to theory of structures, here which is the main part of a prologue. So here I'll be covering all the concepts in detail and solving a lot more problems. I do believe that this will serve as a good foundation for what we are gonna do ahead. So in the main series, let's look into a very basic house, but cover all the aspects of it from substructure to superstructure. Before moving on to more complex projects like commercial buildings, multi-storied buildings, shopping centers. Once we are done with this, let's look into other types of structures as well, like bridges, different kinds of bridges, and roads and sewage system. Everything which might help you get more employment opportunities in the UK. And I also believe they will open up new doors for you, like freelancing, or if you want to open up your own firm. There is a skill gap between when the graduate just passes out and what is actually required by the employers in the industry. So we are trying to bridge that gap and send graduates into the field confidently. And I do believe that knowledge never goes to waste. So let's not waste any more time and move on to geomechanics. So in this series on geomechanics, we'll cover essential topics like stress, Mohr circle, strain and elasticity, yield criteria, slope stability, lateral earth pressure, and retaining walls. We'll wrap it up with one-day flow. And before we start, make sure you review your preliminary mathematics, particularly matrix addition, subtraction, multiplication, and transposition, as we'll be using this in our calculation. I'm doing one basic matrix problem as well, so that you'll get a good idea of what's going on. So let's begin with the concept of stress. So stress is basically defined as force per unit area. Okay, so imagine cutting through a rectangular solid mass like a block of soil. So stress is calculated at this imaginary plane within the material. There are three main types of force stresses that can act on this plane. Okay, so the first one is normal stress. So in normal stress there are two types of stresses, tensile and compressive. So here in this figure we can see that force is being applied on the two surfaces, the top and bottom. So if this area is considered A, then the force considered as P, then stress is equal to P by A. Okay, so yeah, moving on. So depending on the direction, so the stress is either compressive or tensile. So in case of tensile, the stresses will be pulling the material apart, and in case of compressive, the stresses will be pulling the material together. So you can also see this in a change in dimension as the length has increased and here the length has decreased. Okay, so next we'll be moving on to shear stress. So this stress, it actually acts parallel to the plane and tends to cause the material to slide or deform along the plane. So in this next figure you can see that how a force is broken down into its vertical normal force and horizontal components. So now let's talk about setter point. So, unlike stress on a plane, which focuses on forces acting on a single surface, stress at a point considers forces acting in all directions. So, like on a tiny imaginary cube, sail or rock, at a specific location. So, this analysis actually it helps us to understand how the forces are distributed within the material and predicts its behavior under various conditions. So even here we can see that wherever you can see that tau xx, tau yy and tau zz, these are the normal stresses, and tau xy, tau xz, the same here, tau xy, tau xz and tau zy, tau zy. So these stresses they are acting along the surface of the plane and they are shear stresses. So, just for a basic definition, we can say that the which acts perpendicular to the specific face of the cube and can be compressive or tensile. This is normal stress. The stress which acts parallel to the face of the face of the cube and it can act in any direction on each face. This is shear stress. So, in our figure, tensile stress is depicted with arrows indicating the direction. So remember that tensile stress is positive and compressive stress is negative, and shear stress is positive if both the phase and direction are positive or negative. Otherwise, it is negative. So we'll take this as a brief note. Tensile stress is positive and compressive stress is negative. Shear stress is positive if both the phase and direction are either positive or negative. Otherwise, it is negative. So this we will be requiring while solving problems. Moving on to the next slide. Okay. So these stresses can be represented in a matrix which we will explore further. So next we are moving on to principal stresses. So what is principal stress? Principal stress is the maximum or minimum normal stress acting on a plane that has normal shear stress acting on it. So imagine a small cube of material subjected to forces. Okay, so at any given point within this cube, there are infinite planes on which we can calculate stress. So, however, there are specific orientations where the stress is purely normal and there is no shear component. So, these are the principal stresses denoted as sigma 1, 2, 3. Sigma 1 can be the largest normal and sigma 3 can be the smallest normal, and sigma 2 lies in between sigma 1 and sigma 3. So here we can see that this is just a normal cube and there is a tensile stress acting on y direction, tensile stress acting on x direction, and there is also a shear component of xy. So this is the normal cube, and here we can see the same cube is represented on a principal axis. So here there is no shear component. This is the y and x axis and it is at an angle of theta p1 to x. So in this principal axis we can see that there is only two force components, that is sigma 1 and sigma 2. So as I told you, sigma 1, 2, 3, that is for a 3D case. So sigma 1 and sigma 2, this is for a 3D case. So this is lying on its principal axis and there can be a few more principal axis as well. So during this orientation we can see that there is no shear component, just the normal stress components. So we use a process called diagonalizing the matrix to find the principal stresses. So yeah, sigma 1, 2, 3, this is for the 3D case. So sigma 1 can be the biggest, sigma 3 is smallest, sigma 2 somewhere in between 1 and 2, 1 and 3. Okay. We'll be using the matrix diagonalization process, which transforms a given matrix into a diagonal matrix, nothing else. So this simplifies various operations and analysis. Okay. So let me talk about the matrix diagonalization process. So this is just a brief reference for you to follow the step-by-step procedure on how to solve this. Just have a look through it. So what we're going to do is find the eigenvalues, find the eigenvectors, form the diagonal matrix, construct the eigenvector matrix, and diagonalization. So I will solve one problem for you, so it will become more clear for you. And moving on to the final topic in stress, it is invariance. So here in invariance, I'll be talking about how, like, in there are the properties of stress tensor keeps changing as the coordinates getting keeps changes, but there are some properties regardless of the coordinate system, these properties do not change. So these are the three primary stress invariants. First invariant is the sum of normal stresses. So it is representing mean normal stress or hydrostatic pressure. So I2, this is the sum of products of normal stresses minus square of shear stresses. This also I will be showing you a small problem so that you can look at the equations and get a more clear picture. And the third invariant is the determinant of the stress tensor. So this is also related to volume change under stress. So thank you guys for sticking till the end. Hope you enjoyed the video and it has sparked some interest in structural engineering for you. So I'd like to take this time to thank my sponsors, Edifica Advisors. So they're a lovely startup based in London and they operate from multiple locations around the world. They are providing project management and consultation services. Uh, Highly recommended by me. Do check them out. Link is in the bio. Moving on, I'll be uploading two very small videos, two problem videos, one on matrix diagonalization and invariance. Before moving on to the next topic, which is strain, do let me know if you have any doubts. So until the next time, ciao ragazzi.